daylights out of this, and then we'll quit. Good. So, all right. So the first thing is, what is a motor? And there's been a lot of stuff in the literature. This, something moves and it's a motor. But I want to talk a bit about what might be a sensible definition. And if you look at the dictionary, it just says anything that produces or imparts motion is a motor. But I don't think that that sort of makes sense, because by that definition, a bowling ball would be a motor. And I think we can all agree that it probably is not. All right. The authoritative Oxford English says that a machine that supplies motive power for a vehicle. Okay, but by that definition, the sail on an ice boat, these are wonderful things, by the way, would be a motor, and I think it is not. Okay, so what is a good definition of a motor? This is something that I'm really sort of pushing hard. That a motor is a device which uses energy, but not momentum from the outside to cause motion. So I think that that's kind of the key idea. All right, so what's an example of a motor? What's in your car is an example of the motor. And all you do is you put in energy, and it goes. And so this is a motor. How does it go? And at the risk of being rather elementary, the car convinces the road to exert a force on it and push it forward. And so it's pretty magical, actually. So I think this is the idea. And so what a motor should do is it should cause one part of the system to exert a force or torque on another, causing motion. So that's the ticket. So I like to use this kind of as a definition. Okay, so now I want to tell this little story about a really mysterious thing that happened in the world of liquid crystals. And it goes like this. So if you take a liquid crystal cell and you organize the surfaces so that the molecules are perpendicular to the surface, the director is horizontal, everybody's happy. Now if you apply an electric field parallel to the surface, then the molecules will want to align with the electric field. But it turns out that you have to apply a kind of a critical electric field big enough to overcome the elastic forces. So there's a transition called the Friedrichs transition. So you have your undistorted liquid crystal, not shown here, all the molecules are horizontal. You apply a field pointing this way, vertically, and you turn up your whatever voltage source, and when the field is big enough, then the liquid crystal starts to burn. And the same thing happens optically. You apply, you shine light on a liquid crystal cell, which is vertically polarized. It turns out that you have to get to a critical intensity before the liquid crystal starts to align with the optical field. And I talked a little bit about this. And so the way it works in the case of optical fields, photons are actually displaced. And so when they go through the liquid crystal, and because of this change of the extrinsic angular momentum, they exert a torque. And it's kind of like this little cartoon of a periscope. This could be a molecule that displays photon, exerts a torque. Okay. So the way this works is that the optical torque per volume is just D cross E, which you can figure out. And then when the liquid crystal gets distorted at this critical intensity, the elastic torque associated with the molecules not being parallel is balanced exactly by the optical torque, and everyone is happy. So this is a simple experiment, optical Friedrichs transition. You can do it, everything works, and everyone's happy. Then this guy Jánosi came about, and he showed that if you put a tiny, tiny bit of dye, almost any kind of dye in the liquid crystal, you can reduce the threshold intensity by over 2 orders of magnitude. And this is a real problem. So you have torque balance without the dye, you have the elastic torque balanced by the optical torque. Now, you put a tiny bit of dye in there, elastic torque is the same, people checked it. You can reduce the optical torque, and you still have the same distortion. So there's a real mystery here. there's got to be some additional source of torque that nobody understands. So some torque has to come from somewhere, and it cannot come from the light because you've decreased your light intensity. It cannot come from that. So this was a huge puzzle. A very long time, people agonized over this. And so the idea is that light causes the director to reorient against the restoring elastic torque, essentially without the transfer of angular momentum. So how can light cause rotation without exerting a torque? So this was a puzzle, and it took something like, I don't know, maybe 7 years for it to get sorted out. And before I tell you the explanation, I want to talk about the work of these two guys, Jacques Crow and Linus Toumian, who came up with this notion of a translational ratchet. I'm sure most of you have seen this, but the idea is this. You have a potential which is periodic in space, like this, so this is potential energy periodic. You put particles in here and they gather on the minima of the potential. Now you somehow turn off the potential. These particles will diffuse equally to left and right. There's no broken symmetry. You turn the potential back on, and everybody goes to the left to get to the bottom of the potential. So by turning the potential on and off, you can drive current without exerting a torque. You're just turning some switch on and off. You can pump particles in one direction. All right. Is there a connection with this liquid crystal problem? And it turns out that there is. And so this is a kind of a simple cartoon explanation, but imagine the following. Suppose that the dye molecule in its ground state is just some spherical ball that doesn't do anything to the liquid crystal, but it has inside an absorption dipole moment, which can point any way it likes. And when the incoming light is in the same direction as the absorption moment of the dye gets photo-excited into some state, which is now capable of interacting with an amount. So this guy swims around. When it lines up the right way, it absorbs the light, it extends, and now it interacts with an amount. How does it work? Well, this guy wants to align with aromatic molecules. The aromatic molecules want to align to it. So this guy is going to start to rotate towards the aromatic and also exert a torque on it. So the idea is that because these newly created pneumatic molecules are not in the same direction as the original molecules, there's going to be a torque exerted on the pneumatic. And then of course, because there's a torque, these guys are going to rotate, and so they're point sources of vorticity, and so they rotate, and there's going to be a net current which carries angular momentum from the cell walls to the dye. So there's this really interesting story that light only provides energy, but yet inside causes these dye molecules to rotate. And of course, they're photoexcited, eventually they fall back to the ground state, and this photoexcitation falling back to the ground state is like turning the potential on and off. And the potential is not in translation space, but orientation space. So this is kind of a little example of a rotary version of the flashing ratchet. So the nice thing is that these dye molecules are rotating continuously in the same sense, and energy from the optical field drives the shear flow, which then carries angular momentum and all this well. So it's kind of interesting. And now I'll tell you about a second sort of related one, which is really pretty similar. So here you have liquid crystal cell, now aligned this way, and you have a photosensitive layer of dyes in this first alignment layer. And now you shine polarized light on it. And in this case, you expect nothing to happen because the electric field is along the aromatic molecules, so you think if the field does anything, it should stabilize this configuration. But when you do the experiment, you find this remarkable thing. Laser's off, everything is sitting like that. You turn on the laser, and boom, you find that you get this distortion, you get a twist in the cell, where the molecules here rotate away from the equilibrium position, away from the light. So this is really peculiar. So before the deformation takes place, the optical torque is 0, and so the field is really stabilizing the thing, so where is the torque coming from? And now I want to tell you about a different story that was proposed by Rolf Landauer, one of my heroes. And he came up with this really beautiful idea way before the flashing ratchet story, and he said this. He said, suppose you have a spatially periodic potential, say sinusoidal like this, and again, particles will kind of gather at the minima, and then you take again a stationary, in time, a stationary temperature field. So you basically have high temperature on this side of the valley and low temperature on this side. And now the hot molecules on this side are going to be more likely to be excited and diffuse over the barrier than the guys over here. So this thing is going to drive a steady current of particles. Now look at it, no moving parts, nothing. No, nothing flashing, it's just magnificent. Really, I think this is just a beautiful idea. And in his original paper, he actually showed a propane torch heating up the electrical potential. Okay, so this is a really nice, it's a beautiful idea. You should think about this. You know, you should see if you can find some way to make use of this. Okay, so now the thing with the liquid crystal is just the same. Instead of X, you put a theta there, and you're in business. So you have the dye molecules on the surface. So the surface is an automatic field. There are the minima sitting here, and then instead of temperature, you have an optical field, which has a maximum at some angle away from the equilibrium configuration. And so the dye molecules, which are parallel to the pump, are excited, diffuse over the barrier, and you again have a steady rotation of the dye molecules, and again you have the same story that you have these dye molecules exerting a torque on the pneumatic, and away it goes. So basically imagine that somehow you have a dye molecule in this trans state perpendicular to the original direction, and it will then exert a torque on the pneumatic, pulling it over this way, away from the vertical equilibrium. This guy, meanwhile, will rotate in the opposite direction, the dye. And then when it lines up more or less with the optical field, boom, it gets photo-excited, falls down, some of them will be in the ground state, and the same story continues. So you have, again, rotation of the dye molecules in one sense, in the surface layer, exerting a torque. And you can do the dynamics, you can write down the time evolution of the density of the elongated trans and the bent cis states. So you have orientation of diffusion, you have some kind of drift due to the interaction with the pneumatic, and you have transition rates, you get photo excitation depending on orientation, the trans go to cis and vice versa. So you can model the system pretty well. I won't go through all the details. You can put in the dynamics of the liquid crystal in the ball. So this is just the typical director dynamics for a liquid crystal, the usual kind of form, linear time dependence, because there's no inertia. And then you have a surface dynamics. So just look and see what happens on the surface. You have surface viscosity. And then you have the potential of the surface from the interaction of the liquid crystal with the dye, here are the dye densities. Anyway, you can put all the pieces together, you can get a pretty good model, and this describes what the director does as a function of what time when you turn the field on and off. And this agrees well with experiments, so we can do it. But the point is that this is really a nice story, again, showing how you can make an orientational motor using the idea of Landauer.
Yeah, but are there are also dye molecules that are oriented in the opposite direction? They will rotate in the opposite, in the counterclockwise sense.
Well, sure, but the main idea is that light depopulates the molecules which are oriented, depopulates the vertically oriented trans configuration. So these guys just get blown out of there, and they go every which way, but a bunch are going to end up being horizontal. Right?
But the average angular momentum transfer current will be zero? Must be zero. Right?
No, you got a net current
But I don't think some molecules will rotate towards light in this sense, and the other ones will rotate.
But there is a symmetry breaking at the beginning. The director goes one way or the other, and after that, everybody from this horizontal thing is going to go in one sense.
Okay, because he's starting in the pneumatic state.
That's right, yeah.
Okay, that's what.
So it's kind of like, once that it can go either way, but once it starts, you have broken the symmetry. And there'll be other examples that are similar to this. Okay, so this is just some interesting molecular motors that I think are light-driven, and they satisfy the criteria for motors that I had before. And it's interesting that you get this steady unidirectional rotation, which then drive bulk currents. And this is another really interesting question, I think, is you apply a point torque to a fluid, so there's no net force on anything, but eventually that point torque, source of vorticity, ends up somehow evolving into bulk mass translation, where there have to be real forces pushing material around. Okay, now here's another experiment by Hiroshi Yokoyama and Yuko Tabe, and this is kind of a nice experiment I thought I'd tell you about. And basically what they did is they put a monolayer of chiral molecules on top of water and glycerol. And so these are basically, these form a single layer, so it's kind of like a symmetric phase. And they are tilted because that's how they want to be. They're happiest when they make some small angle with the surface normal. And they are chiral. And now what happens is that water molecules evaporate, and as they go, they drive the rotation of these guys. So here's a picture. Again, I don't want to go into the details, but basically what you see here is that as time goes on, and there's a flow of water molecules through this monolayer, it causes these things to spin and precess, and it turns out that if you look carefully, you will see bulk flow. Now, this is between cross polarizers, so what you're seeing is kind of the different orientations of the C director, the projection of the molecules on the surface. So, and then they have really analyzed this.
And the bulk flow is the rotational?
Yeah, you end up with bulk, and I don't have good illustration of that, but there are places where they put little tracer particles, and you can see them moving. So again, it's so point sources of vorticity and
but it just it's the precessional part. It's not just like the rotation of the molecule. It's the precession of its angle. I'm a little confused on that. Initially, there's just a rotation of the molecule, and then this ends up being precession. But because adjacent molecules rotating are kind of rubbing against each other, so the vorticity diffuses, and this ends up translating into vorticity. And again, so you can actually distinguish between clockwise and counterclockwise rotation, depending on what comes out of the middle, a black thing or a white thing. I see, so that's making a vortex dipole, that one on the lower left.
I think this is running,
Looks like
but it's running slowly. All right, life is short. You can imagine what happened, right? Bright thing will come out of that. Here we are, sorry, you can see the white thing coming out. Okay, so main thing is that you can tell the difference between clockwise and counterclockwise rotation, and this is what happens if you, maybe it's better to see it here. If you put right-handed molecules, one thing happens. You have the middle is bright, very bright and not so dark, and this guy does the opposite. So by looking at the intensity in the middle, you can tell which way the thing is spinning. And the precession speed depends on the pressure difference on the two sides. And so it turns out that right-handed molecules spin the same way with the current flowing downwards than left-handed molecules with the current flowing upwards. And so, you know, this is basically the frequency of rotation, which you can get from the evolution of these interference patterns as a function of pressure. And when you change the sign of the pressure, it changes the handedness of the rotation. And this is true both for left and right-handed molecules. Okay, so this is interesting. And then you can get some kind of dynamics basically by knowing that there's a coupling of the rotation of the C director with the current and vice versa. So this is kind of the usual story. And now there are some other experiments that have been done that are kind of interesting where you have a cholesteric liquid crystal which is handed, you take a droplet of that, and if you put that in a temperature gradient, it will rotate. You put that in an electric current, it will rotate. So there are sort of equivalent scenarios here, and you can do dynamics basically by writing down the dynamics for the C director, again, torques coming from the bulk, and a coupling to the pressure gradient, and this is this sort of phenomenological coupling constant, and this is the free energy, pretty much like you would expect. And you can do a simulation, and you see something pretty close to what you would expect. So this is the azimuthal angle, so this is the angle of the C director as the thing evolves.
So if you had a mixture of particles with different two chiralities, then you'd get some sort of phase separation.
Blow up. I don't know what would happen. Actually, they haven't done that, I don't think. But that's a good question. So you think maybe they would phase separate?
Well, if they did, then
domains.
maybe the dynamics would be phase separate too.
But well, that's interesting.
I'm just thinking about having a system where you can produce like some sort of complicated vortical field. You know, vortices of different signs.
That's a really good idea, actually. I'll talk to you. Okay.
Peter, what's the physics of this Lehmann term?
Sorry, Mike?
What's the physics of this last term?
What is the what?
What is this?
C cross.
What is this term?
Yeah.
Well, this is just this is a phenomenological thing, and this is just the torque exerted on the C director due to the current, due to the pressure gradient. But you know, the details of that are not given, but you can actually imagine how that could work if you know, it's kind of like a little windmill thing. You have a kind of tilted plane molecule with exerted torque. Okay, so this was another motor. So this combination of the substrate and the monolayer, I think, is a motor. The energy is coming from the chemical potential energy of water. Come back to that too. So it drives rotation of these chiral molecules. And then again, the interesting thing I think in one sense is that it produces circulating flow. So all you have is local torques, and yet you end up with mass flow and dissipation. Okay, now we're going to tell you about a motor that absolutely blew me away when I first came across it, and many of you might know it. How many people know this ATP synthase? Okay, so the fact that such things can exist is just absolutely mind-blowing. So the idea is that ATP is the kind of unit of currency of energy transfer. So this is the energy source of almost everything in biological systems, and it's made from ADP, which is kind of the low energy version of this guy, and you have to add an inorganic phosphate to it to kind of put the energy in there. And the F1F0 synthase is a motor that accomplishes that. And here's what it looks like. So in every cell there's mitochondria, which generates the ATP, and this motor looks like this. So this is the wall of the mitochondria, and this is a real electric motor. Right? So this central shaft here rotates because of proton transport through here. So essentially electric current flows through here, drives this thing, and as it rotates, it takes ADP and phosphate and makes it into AT. Who would have thought?
That's the same as the bacterial flagellar motor?
Hmm?
Like, that's the same type of motor as the E. coli bacterial flagellum?
I think that's right. They have the same structure up here to rotate. So, yeah, so this guy goes around, and then part of this stacker housing, you have these little pieces, and the ADP and the phosphate go in there, they get squeezed together, made into the high energy ATP. So, I don't know, for me, just to realize that such things exist and work day in and day out, it's really amazing. So basically, the idea is these things just get squeezed together. Now it's in a high energy state, and it can go deliver energy where it is needed. And so, I thought it was interesting that a normal human being produces 100 pounds, about your body weight of ATP every day. Doing this without having to worry about it. Yeah, so these Hoyer and walking without bicycles. Okay, and you know how it works is actually pretty complicated. I mean, but the idea is, I guess, that you have glucose and it's metabolized, and high energy electrons are transported to the membrane, and there you have the energy of these high energy electrons causes the transport proteins pump the hydrogen, the protons outside of the mitochondria. So now you have a voltage difference, and then they go back in through here, and in this transport process, they drive the rotor. And so, again, I don't want to spend too much time on the details, but the fact is you can actually model it relatively well just by writing down some kind of free energy as a function of the angles of all the pieces on the rotor, and have some kind of spring Coulomb potential to describe the forces between the various pieces. And so this is kind of the detailed version of what happens, but anyway, I don't want to go through it, at least in part because I don't fully understand it. But somehow the idea is that you have hydrogen flowing through here, and then you have electrostatic attraction, which exerts forces, which causes rotation, and you go through this cycle, and as the proton goes through this, you end up in the same state, except this guy, as part of the rotor, has not rotated from this condition to this. So, all right, so here's another rotary molecular motor written by proton current from stored electrochemical potential that you make by using a glucose. And then you have ATP, and then ATP can go to various other places in the body. And I just wanted to mention these other motors, and I'm sure most of you know about this. So there are kinesins and myosins, and there are much better movies on YouTube than this, but this kind of illustrates what happens. So there's a kind of a hand-over-hand motion as these heads move along, and it's directional motion because the ends of the microtubules are different. So there's a vector implicit in here. And then there's actin and myosin inside muscles, and it's the same kind of story. You have these myosin heads walking along the actin, pulling this tissue along, and this is a sarcomere, and so these bits get pulled together as the myosin heads move towards the end. And this is a muscle fiber, and they always move in one direction, and so to undo it, you have to use some other muscle to pull it apart again. So it's kind of interesting that, you know, this muscle closes, but I need another muscle to open it up again. I read once that muscles can only pull, but the tongue can push, but I don't know. I think that just has to do with some kind of funny container issue. Anyway, muscle movement. So these are all all processive motors with unidirectional translation, hand motion, and they are driven by the energy of ATP. They hydrolyze ATP as they go, and they move cargo against the force, and again they also dissipate energy. All right, that's it. No, there's one more. So we already talked about elastomers. I don't want to say too much. You know the structure. There's some crosslink network with mesogenic pieces inside, and if you change the order parameter, you have expansion or contraction along the director, and the opposite in the two transverse directions. So if you increase the order, these guys separate, the thing gets longer and skinnier, but if you decrease the order, then it goes the other way, and you get little short, stubby guys. And so one can then use this shape change to make motors. So these are kind of elongational motors, change in orientational order produces stress, stress produces a change in shape, and you can drive this by heat, light, or by adding some chemicals in the 30s. And again, you get motion against force and dissipation. All right. So I wanted to say a few words about broken symmetry. Once again, everything is pretty much a tensor of rank something. And so, I don't know, I like to think of this as follows. So, vectors are things that really exist. So, gravity, for example, is a vector pointing downwards, and it's independent of coordinate systems that I may choose. So, the vector exists, I choose a coordinate system. In that coordinate system, the components of that vector will have some values. If I change my coordinate system, those values change. The vector didn't change, just my representation of my coordinate system changed. So there are these God-given quantities, whatever, scalars, electric fields, tensors, and so on. And if I take my coordinate system and I invert it, so x goes to minus x, y goes to minus y, and so on, then for a proper tensor of even rank, the components shouldn't change. But for a tensor of odd rank, they should change. So I have gravity, and I have a coordinate system with, say, x pointing down this way, the x component is positive, but now if I invert that coordinate system, x is pointing up, the thing will become negative. So that's the idea, and so to determine whether something is proper or improper, you need to check its rank and see what it does under inversion. So there's interesting pseudo-scalars with change sign under coordinate inversion. Seems odd that a number can do that, but if you take the dot product of a proper vector with the cross product of two other proper vectors, then you get a pseudo-scale. And in this case, two wrongs do make a right. So if you take the dot product of two pseudo-vectors, you get a proper scale. So it works as it is. Okay, so how is this relevant? So the symmetry of the system determines the motion of the motor. So it's interesting to ask yourself, what do I have in my system that I can use to figure out what the motor will be capable of doing? And I don't know if you guys have noticed this, but if you have a carpet in your house and you put a throw rug on it, but after a while that rug is going to move quite a long distance. So you notice that in a day or two, that rug will have moved maybe 3 feet or something. It's pretty impressive. And so I was looking for this, and I found this thing on the web. My rugs are alive and moving. And how can I stop them? Is it caused by static electricity? So if you look at a typical carpet, it will have strands which are tilted, and if you put something on top of it, like, this is my little movie and it's not very good, but imagine that you put something on here, a piece of wood or a carpet or something, and you push down, then you're going to bend these fibers, and because these fibers are kind of digging into this thing, they're not slipping on the surface, so they're translating this thing to the right, and so the thing moves to the right. But when you take the load off, it more or less stays there, because the fibers can slip easily in that direction, but not in the forward direction. So by this repeated pushing up and down, you end up with translational motion. And so what is the point? The point is that in this system, you have a proper vector. You look at the direction of the strands, they're fixed at the bottom. You can form a proper vector in the horizontal direction. Once you have the vector, you can have motion in that direction. Okay? And the same thing is true in the case of kinesin and myosin, broken left-right symmetry. But in other systems, you don't. On the other hand, in some systems you have broken chiral symmetry. So if you have a pseudo-scalar existing in the system, then you have chirality, and then you can do, you can look at things of chirality and translational symmetry, and so if you have a pseudo-scalar and a proper vector, in the case of the Yokoyama-Tabe experiment, then you can make a pseudo-vector just by multiplying these together. And rotation is a pseudo-vector. Angular momentum is a pseudo-vector. It's a cross product of two proper vectors. So by looking at the things that you have, you can figure out the kinds of motion that you could possibly have. Now, I wanted to give you guys a little challenge here. So I told you this Landauer story, which I think is really gorgeous. So here you have a potential U of x, which looks like this. So suppose that U is something times cos kx. And then you have a temperature field, and it's slightly shifted from this. So it looks like, I don't know, this. So it will be, so let's call this U naught, T naught, and it'll be cos kx plus 5. And I claim that you can get motion, you can get a current flowing either in this direction or this direction. So that means you must be able to make a proper vector from these two quantities. So your job is to do that. Okay, so see if you can make a proper vector from this. So we just take the gradient of this, it's going to be a sine. It's going to be changing sign everywhere. So the average you'll get nothing. You want to make a proper vector, okay, whose average value points in some direction. Okay. All right. I should give a prize for the first person. All right. So now in the case of a liquid crystal elastomer, all we have is a dyad, so we cannot have translation if that's all we have. So we can only have an elongation. You can have motion in one of two directions, so that's good. If you have a dyad and a gradient, the gradient is a proper vector, then you can make another proper vector from these two, and then you can have curvature, you can have bend, and if you have a proper dyad, proper second line gradient, and a pseudo-scalar, then you can make a pseudo-vector, and you can have twist. So I think just by looking at the symmetry elements you have, okay, just list all the things that you have, and then you can figure out, more or less, what kinds of motions possible. Translation, strain, rotation, twist, bend, and so on. So I think it's nice to think about these symmetry ideas to figure out the kinds of motion that motors are capable of. Okay. So now I want to move on to macroscopic scales. So cumulative effect of many molecular motors can result in a macroscopic response. We see bulk reorientation of the liquid crystal in the optical case. In this rotating dye system, the distributed local vorticity gives rise to bulk rotor flow. ATP synthase produces bulk ATP. Myosin and actin, these little individual motors all group together to form big muscles which can contract. And again, in this elastomers, you can have these strains on a microscopic level which combine to give you large-scale bulk motion. So I want to switch on to the macroscopic level. Now, are there any questions or comments on what I've said so far? No. Jokes, humorous comments?
Have you seen the little toothbrush type, speaking of motors, the little toothbrush type devices?
That's right.
That's similar physics, right?
Yeah, you can buy these little bugs that run along, and I've got one, and I think you're supposed to get two of them and make them fight. You put tethers on them, and yeah, they basically vibrate, but the legs, you know, have essentially a vector associated with them, so they want to go forward or forward and sideways, and then by controlling the tethers, you can make them do it. That's the interesting stuff. Okay, so all right. So I want to talk about now macroscopic object, and I want to focus on smooth shape changes. You know, at first I thought that motors that are based on shape change are really interesting. And then I started thinking about other motors, like really a gas engine, you know. But then you realize that's also shape changing too. You know, the piston's up here, a little later the piston's down here. All that happened is the shape change. Propeller on a ship, the shape of the ship, the propeller turns, now it's a new shape. So everything pretty much is associated with shape change. But in some situations, you have one surface moving against another, so the deformation gradient diverges. And so I kind of would like to focus on systems where there are no such divergences, where we basically have smooth, continuous objects, where the deformation gradient is smooth everywhere. Okay, so this is the sort of little canonical example I was showing you before, and we understand pretty well how this works. And this is clearly a motor based on elongation. Right? So all you're adding is energy by heating it, and it's clearly causing motion. One part of the system exerts force on the other. Okay, so this is a nice elongation-based motor, and there are other ones that you're probably familiar with. So there's the famous rubber band engine. So how many of you have seen this? Everyone should have one in the lab. So the idea is that the spokes are made of rubber. You shine light on them. The rubber contracts. This is just ordinary isotropic rubber. The rubber contracts here. The center of mass moves up here somewhere. And now it's kind of top heavy and it falls down. So this guy rotates continuously like that. I had a visitor once, and the visitor was from the Landauer Institute, and he said that he knew somebody, whose name I cannot remember, who had gone to Siberia, where he was shown a motor which looked like this, except the spokes weren't made of rubber, but they were made of linen. And there were no lights, there was just a bowl of water at the bottom. And apparently this thing rotated continuously. You can imagine that that could work. Water gets sucked up along the fibers, somehow causes contraction, the same kind of thing. But it's a nice idea. It'd be nice to have one of those. All right. Here's another motor based on elongation that was made by Aaron Michalski, who's a brilliant guy. He was a stat mag guy. Okay, so he took collagen, and collagen's in connective tissue all around in our bodies. If you have scurvy, your collagen tends to break down. That's what happens. And all right, so what happens here? So collagen is a protein with a triple helix, and when you expose it to salt ions again break down the hydrogen bonds, and there's a helix to random coil transition, and so the collagen shrinks and gets fatter. So that's what happens here. You have salt solution. The collagen contracts, and now you have sort of high tension here and here, but there's a bigger lever on here, so this guy wins, and this thing turns in this direction steadily, and then the salty bits of the fiber go into the fresh water, the salt comes out, the thing expands, and away you go. So I think this is really a beautiful idea. Here's a modified version where you have these conical pulleys, and this is salt water, and the fiber comes in, and it wants to get shorter. To get shorter, it should work its way down here. You can do that by turning these guys, so it doesn't. And here's a picture of a working model. That was set up somewhere in this room. Okay, so these are nice ideas of elongation based motors. And now here's a really magnificent motor. I love these things. So this is a heat engine, right? So you all know how this works. How many own one? I have a bunch of these. They get old, you know. There's an aging process. And I had one in some outreach thing. The beak got torn off, and so there's just a kind of a black hole there. You know, it reminds you of the screen painting. Anyway, I christened this dunking bird of the first kind because we made one. A dunking bird of the second kind, and I'm really proud of this. I think this is a piece of work that I'm really happy about. And so now this is not a heat engine, right? The original one is a heat engine, works at temperature to the tail on the head of the bird, but this is not. So this is basically just a sponge, a triangular piece of sponge, and when it's dry, the thing tips forward, and the head of the bird goes into the water. And then the water gets sucked up into the sponge, it becomes heavy, sort of tail heavy, and it tips out of the water, and then it dries, and it does it again. It works beautifully, and it's completely isothermal. And it works on the chemical potential of condensed water versus water vapor. And you know that water would rather be a vapor, that's why it evaporates. And it turns out that the stored energy in a cup of water is about what it would take to raise that cup 12 kilometers. The energy stored in the liquid versus vapor water is about the same as fully charged 9-cap batteries of the same mass. It's astonishing. And the only problem is you can't get it out fast enough. That's the problem. If you could pull it out fast enough, you can just pour a glass of water in your laptop. All right, so this is another engine that involves shape change because the sponge swells. Okay, so these are all. So these were all elongational motors, and now I want to talk about bend motors, and you've seen this already, so I won't show you this. But so this is a live-driven bend thing. Maybe you haven't seen this done, but that's okay. These are elastomer things. You shine light and then they curl up, just straighten up. Go. Okay, another one. You've seen this, you've seen this, you've seen this, you've seen this, but you haven't seen this. So this is another one that's made by Tomiki Keita, and so you shine light on it here. And again, it's got different segments, but because of this, it's really articulated, and you can make it do all kinds of clever things. So this is another band motor that works
How
well.
big is it?
Sorry?
What are the dimensions of that?
Oh, this is like centimeter, 10 centimeters size of it. And I have, Tomiki and then his student who's now at Shanghai have really made beautiful things, including things that pick up things and do all kinds of things based on the same material. Okay, and then Tomiki made this motor, which I really like. And so this is just 2 pulleys and a little crystal elastomer. And you shine light on this, and it goes around. And now this is something I really wanted to understand. Right? How does it do that? Where does the angular momentum come? So, all right, so what I really want to focus on for the rest of this talk is to understand how this guy works. But there's a similar device made from nitinol, nickel titanium alloy, which undergoes martensitic transition from orthonomic martensite to cubic austenite when you heat it up. How many of you have seen this? I have one here. I can show it if you want. You want to see it?
Yeah. Sure.
Okay, then I need a glass of hot water. Maybe this will be hot enough. Let it run for a while, see if it works. If not, we'll need something else.
Need a glass?
I'll have a glass.
Or-
I'll have a cup. And so the interesting thing about this material is that the high temperature phase is stiffer than the low temperature phase by about a factor of 3. So we understand that the liquid crystal elastomer bends on exposure to light, and it bends because if you have a layer, the top part contracts more than the bottom part, so it wants to bend. This guy, the wire just gets stiff when you heat it up. Okay, so what I want to do is I want to understand these 2 motors in some detail. So the first idea is this. We have a piece of material, some slender elastica, and like a ruler, and I take the ends and I push them closer together by a distance delta L. What will it do? Well, it can do one of 2 things. It can bend like this, or it can simply compress. And you can calculate the energy first by figuring out what the radius is if you have a change in length of delta L relative to L. And then you can figure out the bend energy just by looking at the elastic energy, stretching the top and compressing the bottom. So it ends up being this. And if you just compress it, it ends up looking this, just 1/2 the modulus times the strain squared as volume. So if you compare these 2 energies, you see that the compression over the bend blows up if the thing is really slender. So that means that the energy cost typically of bending is so much cheaper than stretching that one can assume that the length of these filaments is constant. All right, so we made a model, and this is just to kind of parameterize it a bit. So we both of these motors are 2 pulleys, and one puts this filament around it, and the thing is in contact over a portion of the pulley, and not in contact, it has some arbitrary shape in here. If you do a straight line, it is easiest. Then again, it's in contact, again, not in contact, and like that. And so S is arc length along the filament, R is just some position vector, usual coordinate system, X, Y, Z is into the board. And the band energy is just what we had before, basically goes as the curvature squared. This is Young's modulus, and I is just the moment of area, goes as the thickness cubed or something. So just call it a stiffness constant, and 1 over R is the curvature. So that's the band energy, and that's all there is in this material. So that's all we have to worry about. It's getting cold. All right, let's see if it works. If not, maybe we can get farther away. So it's about this big. Warm water.
Is it one? Did you get one wire? Is it one or?
I'm not sure. Let's try it. I don't think it is, but let's try it anyway. So I put this guy in here. Nothing All right. I need hotter water. Can you grab something?
Oh, of course.
It doesn't have to be boiling hot, but it's just warm. Okay. Let me continue. So write down the total energy. The idea is to write down the energy and then minimize the energy, and we'll learn something. So going to break it up into pieces. So starting from here, go to here. Write down the band energy, so stiffness constant, band squared. But the material may want to bend by itself, so there's a natural curvature that you put in here. And then you go on to the free part. And again, this is just the band energy again. So here's the stiffness, except here, we don't know the curvature, so we have to take the derivative of the tangent. And again, there may be natural curvature here, and this is just to make a vector pointing the right way. So basically, this is just curvature, just the same as this, over this portion. Then you go from there to there. You know the curvature is R2. Then again, you go on here, and then back again, that's it. So that's simple. And the main thing is that there are these two parameters. There's the stiffness and the natural curvature. And because we are heating the thing and shining light on it, these quantities may be a function of position. So the stiffness can vary with position, and the natural curvature can vary with position somehow. And we'll put that in by hand. So what's the model? Well, we have the energy, but there are some constraints. The length of the filament is constant, that doesn't change. The displacement in the x direction is fixed. So if I integrate my total x component of length when I get here, I better get just the distance of this diameter, that diameter, plus the stuff in the middle. So there's a constraint in the x direction both for the top part and the bottom part. So this is just measuring the x components and adding them up. And the same is true in the y direction. When I go around from there to there, the total y displacement should be 0. And that's it. So now we can write down the energy and put in the constraints. This Lagrange multiplier, so this could be horrible, right? But it's really that simple. And if you meditate on this for a while, then you realize that these Lagrange multipliers are just components of forces in the top and bottom filaments. The force in the filament up here cannot change because there's no external forces. It's a constant force that's carried all along here. And that just ends up being the Lagrange multiplier. Okay, that's it. And then you just minimize the energy. You can parameterize the tangent in terms of an angle. And then you get some simple ODE with these Lagrange multipliers for the top and the bottom. And then there's still a question of where do we lose contact with the cylinders, so we have to minimize the energy by taking the derivative with respect to these contact points. And what that gives you is the condition is that the tangent has to be continuous and the curvature has to be continuous of the contact points. It's not a big surprise. So that's it. And now one can go ahead and do the numerics, which is again pretty simple, but a little tedious. You have all these unknown quantities, the contact points, Lagrange multipliers. You assign arbitrary values, solve the ODE with the boundary conditions, continuity of things. Do the same thing on the bottom half. And then now you have to vary the Lagrange multipliers to satisfy the constraints, make sure that the endpoints are where they're supposed to be. And then finally vary the contact points until you're at the minimum of the energy. So that means that the curvature has to be continuous of the contact point. So one has to grind away, get this numerics. And then if you put in,
It should be pretty
very good. All right. I'll just put it in there. How hot is it? Melt the cup? Maybe too hot. It's hot. All right, we'll try it again. So I'll put it in. It may be too hot. Anyway, there we go. So it's really pretty impressive. It really goes.
So what
And it's a reversible engine.
do you need to give it a kickstart? Do you need to give it a kick?
Sometimes it starts by itself. You know, if it just depends. If the wire is a little asymmetric, it will start by itself.
It won't go if you stick the big end.
It should go, but I think you need relatively high heat, a specific heat. So I think it's not the size. I think it's the ability of the thing to transfer heat. So it's really a great device. I encourage all of you to buy
So
it.
why aren't you going to try it? Why aren't you going to put the big end in?
There's got to be some suspense. All right, I'll put it in. But it may still go because this is hot, you see. So long, you can just heat this, you can focus sunlight on it, it'll still run. Should we take bets? All right, I put it in. Doesn't do it. But, with this guy, broken. Really?
You put one side in cold water.
There's supposed to be a temperature difference between
Yeah.
the big wheel and the little one. By dipping both now, it probably.
So you put that side in cold
No,
water.
the big wheel is actually cold. I think the little wheel is maybe too hot. Pull it out. There we go. Okay.
If you take a piece of this wire and just let it flat, and then you heat some part of it, you're going to stick with it, is it going to spontaneously bend or anything like that?
Well, you can chain it, right? You can, I mean, so this is a shape memory material. You can chain it, you can put it in a certain shape in the low temperature phase, and then when you heat it, it will go back to the undeformed state. And yeah, and there are liquid crystal elastomers that have a shape memory effect as well, in addition to the mechanisms that we talked about. Okay, let me press ahead. So in the case of the elastomer, where you shine light on it, presumably it wants to bend So we put in an actual curvature for some small part of it near the little wheel, and then you can grind away, get the solution, and this is what it looks like. And now we know everything. We know all the forces everywhere inside the wire. We know the shape. We know everything, and we're happy. And the same thing is true for changing the stiffness. You can dial in the stiffness where the wire touches the wheel, maybe where it comes off it. You can make it stiffer, and so you just put that in, and again you get the solution for the shape of the wire, and you know pretty much everything about it. So now the question is, why does the thing turn? And so one wants to look at the torque acting on the little wheel, and so one good trick is just to consider a part of the system. Okay, so mentally cut it into two pieces, and look at all the forces that you have coming from the wire that you have just cut away, and you get the torques from that. But in addition, because the wire is bent, you also get point torques acting on the end. And so by adding together all the torques from these forces and the torques, you get the total torque. And there's a kind of an interesting thing, which is that if you take the original ODE that you get from minimization, and you integrate it with respect to S, arc length, then you get this little equation that says we had a 0 before, and now we have a constant here. And this thing just says that the torque, this is just the total torque on the wheel, it says that it's a constant regardless of where you cut the wire. And that's a kind of an obvious thing, but I have this thing, there's some physical torque acting on it, and whether I cut the wire here and calculate, or cut it there and calculate, I got to get the same answer. And so a way of getting the original equations of motion I could have done by just simply realizing the fact that there is this invariance. And in fact, Euler knew all about it, but we couldn't read Euler until after we did this. Okay, so this ODE is precisely the condition that the torque on the wheel is constant regardless of where you cut it from. All right, so now we know what happens on the free part, what happens on the pulleys. So this is really where this ruler on the wine bottle problem came from. What happens when the wire goes around the pulley? And so we've talked about this. There's this funny transition that you get. And we studied this experimentally. It turns out that it's pretty hard to get good experimental data. So we took a piece of plastic, and we found that by, this is the cylinder, we apply the force on the ends, and we found that by looking at the reflection of the cylinder, we could kind of see how the transition happened. You can fit these curves, and you can determine the contact point pretty accurately. And so this is some early data. We have better data in here. And anyway, the punchline is that if you look at this carefully, you find that there's a finite contact angle here, which was kind of surprising for us, but now we understand it better, as I mentioned, in terms of this Landauer expansion. So not a pitchfork bifurcation. Okay, then the question is, so what is the force distribution on the pulleys? And so it's straightforward to determine the critical force when the thing splits. And okay, that's basically just equating the curvature of the bent elastica to that of the cylinder. And then you get a torque balance equation if you write down where the torque is at some point here, due to all the material out here. And you got this nice equation in terms of this unknown force density along the contact region. And that turns out to be a Volterra equation of the first kind. And turns out that one can solve this. And the solution is interesting because it contains a singular part. It's got a delta function as well as a continuous part. And well, here's a little movie. So initially, you push down, you only have the delta function on top, and then it splits in two, the critical point, boom, and then you have an increase in uniform force density upwards and the delta function at the edges. So we know pretty well how this works. All right, now the question, how does rotation actually come about? So one can calculate the torque on a little wheel due to all the horizontal forces. So this is the horizontal force in the top filament, bottom filament, the sum of those. And this is the distance from the center of the little wheel. Okay? And so you can see that these torques vary with position. This is the torques due to the vertical forces, and this is the torque due to all the point, the bending of the filament. So everybody varies, but if you add them all together, you find that you get the same torque no matter where you cut the filament, as you should. Okay, but this still doesn't tell us where the torque is coming from. And so kind of intuitively, you can think of sort of two scenarios. When you go quite a ways from the small wheel, if you look at the shape of the filament, you see that it's further away on this side than on this side. And although the force isn't constant, it's more or less constant in this regime. So basically here, what happens is that you just have a bigger lever arm here, exerting a bigger torque on that side, and so the thing ends up rotating in that direction. Alternatively, if you go closer to the wheel, then you see that the curvature of the wire is the same. We said it has to be continuous, and it's the same as that of the little cylinder. But the wire is stiffer over here. So even though the curvature is the same, the point torque is greater because of the stiffness in one case, or because of the natural curvature in the other case. So you can think of either longer lever arm on one side than the other. And if you look carefully, you can actually see the wire pulling away. But in fact, it turns out that that torques play a role even in that case, and forces play a role even in this case. But approximately, I think this gives a reasonable estimation of how the torque comes about. Now, back to this question of how can a point torque give rise to translational motion? There's no net force. How can a point torque give rise to translation? Suppose you take a turntable, record player. You guys don't know what that is probably. You glue a toothpick to it, and you apply a torque to the toothpick. The whole thing is going to rotate. But you're not applying a force. But yet, there has to be a force on the mass which is starting to move. So it's the same problem here. So how can a point torque over here give rise to translational motion? And so one way to think of this, I think, is as follows. So think of that point torque as being a couple made of two equal and opposite forces. And now, if this is all you had, then this guy, this sort of pendulum, would want to rotate, and this point would want to move in that direction. But we have a constraint. This thing is pivoted at the center. So a constraint force appears here to enforce the fact that this point cannot move away. And now, because of this constraint force, we have a net force in the system, and the thing will move. So I think that the motion comes about because you apply a torque, constraint force appears, and now you have a net force, and you end up with translation. So I think that's how the motion comes about. And one thing that we learned from this exercise is that if there was no friction between the filament and the wheel, the thing wouldn't work. So if you were to just take a smooth piece of plastic, put the wire on it, and put lots of oil so the wire would slip, it wouldn't work. So it really needs to have this friction so that this constraint force can come into the picture. Okay, so how does angular momentum flow? So point torque in the filament, as we said, gives rise to a constraint force which appears on the wheel, and then of course the wheel exerts an equal or opposite force on the axle here, and if you're holding this, that appears as a torque. So when the thing starts, torque angular momentum flows in through your hand, you're exerting a torque to oppose the torque by this reaction force. And it's that angular momentum that causes the thing to rotate. So that's how it goes. All right, so we have, I think, a fairly good detailed model of these band motors, both the elastomer one and the Schematic motor. And one prediction of our model is that if you had a liquid crystal elastomer with the director perpendicular, it would run the other way. And Ikeda made such a motor, and it does run the other way. So I think we understand angular momentum transport, but we don't really know what the efficiency of such a motor is. And so here's a picture. So yeah, I started this by saying that a motor is something that should work without momentum flowing into it, only energy. But in this case, you have to consider the entire picture of the earth and me and the motor. And this is now the whole motor. And when you apply the stimulus, the energy, the heat, or the light to the motor, the filament bends. The torque appears. That torque will cause angular momentum to flow into the object because I'm exerting a torque. I have to exert an equal and opposite torque on the earth. Rotation starts and the earth speeds up. And you can try this, and if you listen really carefully, you can feel it. Okay, that's it. So, all right. Main conclusion, so there's lots of molecular scale mechanisms that can be exploited, and I've shown you some of these. I think there's some interesting possibilities here. Symmetry plays a role in determining what happens. Microscopic phenomena, cumulative effects of what happens, and I think we understand these particular kinds of band motors really well. And I want to close with this little cartoon from XKCD, which I like now. Okay, thank you very much.
Questions for Peter? Okay. Lunchtime.
Anyone wants to come and play with it? It's right here. Thank you.